Fractional distillation is the separation of a mixture into its component parts, or fractions, such as in separating chemical compounds by their boiling point by heating them to a temperature at which one or more fractions of the compound will vaporize. It is a special type of distillation. Generally the component parts boil at less than 25 degrees Celsius from each other under a pressure of 1 atmosphere. If the difference in boiling points is greater than 25 degrees Celsius, a simple distillation is used. Laboratory setup. Fractional distillation in a laboratory makes use of common laboratory glassware and apparatuses, typically including a Bunsen burner, a round-bottomed flask and a condenser, as well as the single-purpose fractionating column. Apparatus. Heat source, such as a hot plate with a bath, and ideally with a magnetic stirrer. Distilling flask, typically a round-bottom flask, receiving flask, often also a round-bottom flask, fractionating column, distillation head, thermometer and adapter if needed, condenser, such as a Liebig condenser, Graham condenser or Allen condenser, vacuum adapter, boiling chips, also known as anti-bumping granules, standard laboratory glassware with ground glass joints, for example quick-fit apparatus. Discussion. As an example, consider the distillation of a mixture of water and ethanol. Ethanol boils at 78.4 degrees Celsius while water boils at 100 degrees Celsius. So, by heating the mixture, the most volatile component will concentrate to a greater degree in the vapor leaving the liquid. Some mixtures form azeotropes, where the mixture boils at a lower temperature than either component. In this example, a mixture of 96% ethanol and 4% water boils at 78.2 degrees Celsius. The mixture is more volatile than pure ethanol. For this reason, ethanol cannot be completely purified by direct fractional distillation of ethanol-water mixtures. The apparatus is assembled as in the diagram. The mixture is put into the round-bottomed flask along with a few anti-bumping granules, and the fractionating column is fitted into the top. The fractional distillation column is set up with a heat source at the bottom on the still pot. As the distance from the still pot increases, a temperature gradient is formed in the column. It is coolest at top and hottest at the bottom. As the mixed vapor ascends the temperature gradient, some of the vapor condenses and revaporizes along the temperature gradient. Each time the vapor condenses and vaporizes, the composition of the more volatile component in the vapor increases. This distills the vapor along the length of the column, and eventually the vapor is composed solely of the more volatile component. The vapor condenses on the glass platforms, known as trays, inside the column, and runs back down into the liquid below, refluxing distillate. The efficiency in terms of the amount of heating and time required to get fractionation can be improved by insulating the outside of the column in an insulator such as wool, aluminium foil or preferably a vacuum jacket. The hottest tray is at the bottom and the coolest is at the top. At steady-state conditions, the vapor and liquid on each tray are at equilibrium. The most volatile component of the mixture exits as a gas at the top of the column. The vapor at the top of the column then passes into the condenser, which cools it down until it liquefies. The separation is more pure with the addition of more trays initially. The condensate will be close to the azeotropic composition, but when much of the ethanol has been drawn off, the condensate becomes gradually richer in water. The process continues until all the ethanol boils out of the mixture. This point can be recognized by the sharp rise in temperature shown on the thermometer. The above explanation reflects the theoretical way fractionation works. Normal laboratory fractionation columns will be simple glass tubes filled with a packing, often small glass helices of 4 to 7 ohm diameter. Such a column can be calibrated by the distillation of a known mixture system to quantify the column in terms of number of theoretical trays. To improve fractionation, the apparatus is set up to return condensate to the column by the use of some sort of reflux splitter. A typical careful fractionation would employ a reflux ratio of around 4:1. In laboratory distillation, several types of condensers are commonly found. The Liebig condenser is simply a straight tube within a water jacket, and is the simplest form of condenser. The Graham condenser is a spiral tube within a water jacket, and the Allen condenser has a series of large and small constrictions on the inside tube, each increasing the surface area upon which the vapor constituents may condense. Alternate setups may utilize a multi-outlet distillation receiver flask to connect 3 or 4 receiving flasks to the condenser. By turning the cow or pig, the distillates can be channeled into any chosen receiver. Because the receiver does not have to be removed and replaced during the distillation process, this type of apparatus is useful when distilling under an inert atmosphere for air-sensitive chemicals or at reduced pressure. A Perkin triangle as an alternative apparatus is often used in these situations because it allows isolation of the receiver from the rest of the system, but does require removing and reattaching a single receiver for each fraction. Vacuum distillation systems operate at reduced pressure, thereby lowering the boiling points of the materials. Note that the use of anti-bumping granules will not work at reduced pressures. Industrial distillation. Fractional distillation is the most common form of separation technology used in petroleum refineries, petrochemical and chemical plants, natural gas processing and cryogenic air separation plants. In most cases, the distillation is operated at a continuous steady state. New feed is always being added to the distillation column and products are always being removed. Unless the process is disturbed due to changes in feed, heat, ambient temperature, or condensing, the amount of feed being added and the amount of product being removed are normally equal. This is known as continuous, steady-state fractional distillation. Industrial distillation is typically performed in large, vertical cylindrical columns known as distillation or fractionation towers, or distillation columns with diameters ranging from about 65 cm to 6 meters and height ranging from about 6 meters to 60 meters or more. The distillation towers have liquid outlets at intervals up the column which allow for the withdrawal of different fractions or products having different boiling points or boiling ranges. By increasing the temperature of the product inside the columns, the different hydrocarbons are separated. The lightest products exit from the top of the columns and the heaviest products exit from the bottom of the column. For example, fractional distillation is used in oil refineries to separate crude oil into useful substances having different hydrocarbons of different boiling points. The crude oil fractions with higher boiling points, have more carbon atoms, have higher molecular weights, are more branched-chain alkanes, are darker in color, are more viscous, are more difficult to ignite and to burn. Large-scale industrial towers use reflux to achieve a more complete separation of products. Reflux refers to the portion of the condensed overhead liquid product from a distillation or fractionation tower that is returned to the upper part of the tower as shown in the schematic diagram of a typical, large-scale industrial distillation tower. Inside the tower, the reflux liquid flowing downwards provides the cooling needed to condense the vapors flowing upwards, thereby increasing the effectiveness of the distillation tower. The more reflux is provided for a given number of theoretical plates, the better the tower's separation of lower boiling materials from higher boiling materials. Alternatively, the more reflux provided for a given desired separation, the fewer theoretical plates are required. Fractional distillation is also used in air separation, producing liquid oxygen, liquid nitrogen, and highly concentrated argon. Distillation of chlorosilanes also enable the production of high-purity silicon for use as a semiconductor. In industrial uses, sometimes a packing material is used in the column instead of trays, especially when low pressure drops across the column are required, as when operating under vacuum. This packing material can either be random dumped packing such as Raskig rings or structured sheet metal. Typical manufacturers are Koch, Sulzer and other companies. Liquids tend to wet the surface of the packing and the vapors pass across this wetted surface, where mass transfer takes place. Unlike conventional tray distillation in which every tray represents a separate point of vapor-liquid equilibrium, the vapor-liquid equilibrium curve in a packed column is continuous. However, when modeling packed columns it is useful to compute a number of theoretical plates to denote the separation efficiency of the packed column with respect to more traditional trays. Differently shaped packings have different surface areas and void space between packings. Both of these factors affect packing performance. Design of industrial distillation columns. Design and operation of a distillation column depends on the feed and desired products. Given a simple, binary component feed, analytical methods such as the Maccabeer-Urothiol method or the Fenske equation can be used. For a multi-component feed, simulation models are used both for design and operation. Moreover, the efficiencies of the vapor-liquid contact devices used in distillation columns are typically lower than that of a theoretical 100% efficient equilibrium stage. Hence, a distillation column needs more plates than the number of theoretical vapor-liquid equilibrium stages. An indication of numbers: the separation of two compounds with relative volatility of 1.1 requires a minimum of 130 theoretical plates with a minimum reflux ratio of 20. With a relative volatility of 4, the required number of theoretical plates decreased to 9 with a reflux ratio of 0.66. In another source, a boiling point difference of 30 degrees Celsius requires 12 theoretical plates and, for a difference of 3 degrees Celsius, the number of plates increased to 1,000. The reflux ratio is the ratio of the number of moles returned as reflux liquid to the fractionating column and the number of moles of final product, both per unit time. See also, azeotropic distillation, batch distillation, extractive distillation, fractionating column, freeze distillation, Raskig rings, steam distillation. References. External links: validating your binary VLE data, chemistry activity, fractional distillation.